In this second part, we will give some more examples of infinitely divisible distributions as well as Levy processes. So let's begin with the following example of a geometric distribution, which is a distribution where you take some parameter p between 0 and 1, and then the probability that your geometric random variables, let's call it g, takes value n is 1 minus p to the n, for n equal to 0, 1, 2, and so on. So for integer n. Okay, let me note here that sometimes g plus 1 is called a geometric random variable. So in other words, its values start at 1 rather than 0. Okay, but here we'll take this definition starting from 0. And then it's not obvious at all in this case that this distribution is infinitely divisible. For example, the sum of geometric will not be a geometric distribution. And so to see that it is indeed infinitely divisible, let's take a look at its characteristic function. So the characteristic function of this distribution, of course, it will be just by definition a sum over all n e to the itn times this probability, okay, which is 1 minus p, and the rest is a geometric series where p is replaced by p e to the it. Now we want to write this as an exponential of something or exponential of its logarithm, so let's take a look at the logarithm of this function, which of course will be log of 1 minus p minus log of 1 minus p e to the it. And using the Taylor series for the logarithm, we can write this as a sum over k starting from 1, p to the k over k in the first term with a minus sign, but in the second I'm going to write the second one, which will come with a plus sign, so this will come with e to the I tk, and this minus 1 coming from the first term. So in particular, we can write our characteristic function as the exponential of this sum. Okay, and actually each factor here, if you look at it, it resembles a characteristic function of some classical distribution, namely a Poisson. So let's recall that if we have a Poisson distribution with some parameter lambda, then its characteristic function will be given by, well, we can compute it again by definition, so it's a sum over k starting from 0. Poisson probability is this times e to the itk. And then we can see that this is e to the minus lambda, and the rest of the series is again just a series for the exponential with parameter lambda times e to the it. Okay, and so in the above characteristic function, if we write this as a product over k of these exponents pk over k e to the I tk minus 1, we can see that each factor here resembles very much the Poisson characteristic function. Okay, namely, if we take lambda pk over k, and then instead of t we take tk, then we get exactly the same thing. So in other words, this is a characteristic function of k times the Poisson, right? So this rescaling of t by k just means that we multiply our random variable by k, where xk is Poisson with parameter pk over k. And since the product of characteristic function just corresponds to taking a sum of independent random variables, this suggests that the geometric random variable can be written as a series over k of k times xk, where all of these xk's are independent, Poisson with parameter pk over k. Okay, and indeed it's very easy to justify that this series is well defined, and indeed when you take the limits of partial sums you have all the convergence that you want here, right? That just follows from the fact that when you take this series, the variance of Poisson is also given by its mean p to the k over k. So the sum of variances will also be a converging series. So we had this Kolmogorov's theorem that shows that this series is defined. And so indeed a geometric random variable can be represented by this series of Poisson random variable rescaled by this k. And so once you made this observation, you can write G as a sum of any number of IID random variables. So these GLs will be IID, where of course each GL, you just have to use the fact that the Poisson xk is infinitely divisible. So in the above sum, you want to replace Poisson xk by xkn with the mean scaled by n, right? So the n copies of the Poisson with this mean scaled by n will recover a Poisson above. And so this shows that the geometric distribution is infinitely divisible. And in fact, if you don't want to deal with these issues about convergence of random series, you can simply stop the sum at some finite partial sum, and then you see that that corresponds to an infinitely divisible distribution, and then you take the limit and use the previous theorem, that the limit of infinitely divisible is also infinitely divisible. So next we will go back and discuss Levy processes a little bit more. Okay, and in particular we will show that there is this one-to-one correspondence between Levy processes and infinitely divisible distribution, which is described in the following theorem. Okay, so in this theorem we show that first, if you have a Levy process and f of t is a characteristic function of this Levy process at time 1, then f to the power c is a characteristic function of a Levy process at time c for any positive c. And by the stationarity property of the Levy process, that means that once we know the characteristic function of the distribution at 1, we know the characteristic function of any increment of the Levy process. So in other words, an infinitely divisible distribution of the process at time 1 determines all finite dimensional distributions of our Levy process. Okay, and in the other direction, if you start with an infinitely divisible distribution and you consider its characteristic function, then there exists a Levy process such that this characteristic function or this distribution is a distribution of the Levy process at time 1. So in other words, for every infinitely divisible distribution, we can construct a Levy process where this distribution is just the distribution of the process at time 1. Okay, so to prove the first statement in this theorem, we notice that it is kind of obvious if you take the time to be rational of the form m over n, right? In this case, then this follows from independence and stationarity of the increments, right? The characteristic function at time 1 over n will be just the nth root, and then at any multiple of that you can combine m independent increments, and that gives you the power m. And then for general C, you can approximate by a rational time. So let's say if we take a rational time from below, so x m over n, and then add the increment x of c minus x m over n. Right, by independence of the increments we can write this as a product, and the first factor here will be by what we said of the form that we want, and then the second factor by stationarity of the increments can be written for the process x at time c minus m over n. And since the Levy process is continuous in probability, this random variable x will converge to 0 in probability, since x at time 0 is 0. So the second factor will converge to 1, and the first factor will converge to f of t to the c, and so we get the same formula for general C. Okay, so this was part 1. And so in part 2, let's start by defining a finite dimensional distribution of this process, so at arbitrary times C1, CD. And let's define it by enforcing the properties that we want, namely independence and stationarity of the increments, right into the definition of these finite dimensional distributions. So in other words, let increments be independent, and let the distribution of the increment be defined by this characteristic function given by this function ft that we are given here times the increment of this parameter c. And so from our discussion above, we know that any power of a characteristic function of infinitely divisible distribution will also be a characteristic function. So indeed there is such a distribution for the increment, and it depends only on the increment of the parameter c. So we have stationarity built in right into this definition, and as well as independence of increments, and so this defines finite dimensional distribution of the process. And what remains to check is that these distributions are consistent, so we can appeal to Kolmogorov's consistency theorem to define the distribution for all c simultaneously, and then we also have to check continuity in probability. Okay, so let's first look at Kolmogorov consistency. Okay, which means that if we add or remove a point in the above finite dimensional vector, then the distributions will agree. So for example, let's say if we remove point Cj from the above construction, then the increment between x at time Cj plus 1 and x at time Cj minus 1, of course, if we write it as a sum of two increments, okay, then we can see that it has the distribution, or it has a characteristic function given by the product of characteristic functions by independence of the increments in our construction. And the first one was of the form f of t to the increment of the argument. The same for the second one. And of course we end up with characteristic function of the same form with the increment of the argument between Cj plus 1 and Cj minus 1. And that's exactly what we want it to be, so we have the consistency. And so by Kolmogorov consistency theorem, there is a process defined for all C with finite dimensional distributions as above. And by our construction, finite dimensional distributions satisfy the properties that we want, namely independence of the increments and stationarity. And so we only need to see why we have continuity in probability. Okay, and this is because the way we define the process, when we look at the increment between time c plus h and time c, right, it has the distribution of the increment has a characteristic function given by ft to the power h, which is the increment of the argument. Okay, and we see that when h goes to 0, this characteristic function goes to 1. And of course that means that this increment converges in distribution to 0, right? Because 0 has characteristic function equal to 1. But we know that convergence in distribution to a constant implies also convergence in probability. So this increment converges to 0 in probability, and that's exactly what continuity in probability means. Okay, so this finishes the proof of this theorem, identifying Levy processes with infinite dimensional distributions. So next we'll take a look at another family of infinitely divisible distributions called compound Poisson distributions, okay, which are defined as follows. If you have a Poisson random variable with some parameter lambda, and you have a sequence XL of IID random variables from some distribution P on the real line. Okay. Then when we look at the sum of these IIDs up to this Poisson random variable, where of course we also assume that Poisson is independent of these x's, okay, then the distribution or the law of a sum of this form is called a compound Poisson distribution. In particular, it's clear that compound Poisson distributions is a subset of all infinitely divisible distributions, right? Because if in this definition you break your Poisson random variable n into a sum of little n independent or IID Poissons with parameter lambda over n, then defining a sum as above for each of these independent Poisson random variables ni of xl I. Of course, you also have to take independent copies of the sequence x for each I, right? Will give you a random variable, let's say yi, such that your original sum is equal in distribution to the sum of these yi's, and clearly these yi's are IID. So this proves that any compound Poisson distribution is infinitely divisible distribution, and the reason for that is that Poisson was infinitely divisible distribution. Now let's also take a look at a characteristic function of a compound Poisson distribution above. Right? If we compute the expectation of e to the it of this sum, now by independence we can first fix the capital N, or in other words, we can sum over all possible outcomes of the capital N, which happen with Poisson probabilities, lambda to the k over k factorial e to the minus lambda. And then when capital N is fixed to be k, we are left, of course, with just a characteristic function of 1x to the power k. And so, as before, we get e to the minus lambda plus an exponential series corresponding to lambda f of t. And then recalling that f of t was a characteristic function of the distribution of x, right? We can write this as exponential to lambda times the integral of e to the itx minus 1 with respect to the distribution of the sequence x. Okay, so we have this explicit formula for the characteristic function of a compound Poisson in terms of its two parameters. right? Namely the mean of the Poisson random variable and the distribution P of the IID sequence. And using this formula, we will now show that any infinitely divisible distribution is a limit of compound Poisson distributions. And in fact, before we prove this, it's easy to explain what the main idea is. So basically, if we have a random variable x from some infinitely dimensional distribution P, as we said, it's equal in distribution to the sum of n IID copies where these xi come from some distribution Pn. And in compound Poisson distributions, we also take sums of IIDs, but up to a Poisson random variable. So here, what we'll show is that if you sum not up to n, but up to a Poisson random variable with the mean n of the same IID sequence from the same distribution, then although n has been replaced by a random variable Poisson with the mean n, actually these two sums are not far from each other. And for large n, this is close in distribution to x. So when n will go to infinity, this compound Poisson random variable on the left will converge in distribution to our x. Okay, and to prove this, we can simply start with the characteristic function of this sum on the left-hand side, which by the formula that we just proved above will be exponential. You have to take the mean of the Poisson, here it's n, and then you integrate e to the itx minus 1 with respect to the distribution of xi's, which is Pn. Or in other words, this is exponential of n, a characteristic function fn of this distribution Pn minus 1, where this characteristic function fn, of course, is the nth root of the characteristic function of our original distribution. And then, as we'll do in a second, you can check that this indeed converges to the characteristic function f of our original distribution. But also, to understand how one can get this idea, we can start directly with our characteristic function fn, and then if we write it as the nth root of our characteristic function to the power n, and then if we write this as exponential of the logarithm, so it will be exponential to n logarithm of ft to the power 1 over n. And then what we'll do here inside the logarithm is add and subtract plus 1. Right? And this is because when you look at the nth root of our characteristic function of an infinitely divisible distribution and write it in terms of the polar coordinate representation, right, we see that when n goes to infinity, because the modulus is not equal to 0, this converges to 1. So in particular, subtracting 1, you get something small. And so in the above exponential, if you just write the logarithm of 1 plus z as a Taylor polynomial up to the first order, so the first order term will be exactly this nth root minus 1, and then you will have smaller order terms, and you just have to see that those disappear when n goes to infinity. And then you notice that the first term here is exactly what we have above. Right? So this nth root of f is just fn of t, and then you have something e to the little o of 1, which goes to 1. Right? And this exponential here corresponds to that exponential of a compound Poisson distribution that we considered above. And then to show this convergence that we want, if we just take a look at this expression in the exponent, and then rewrite the nth root of the characteristic function as e to the 1 over n, the logarithm of the characteristic function. Now, when you write Taylor polynomial for this exponential, you get exactly 1 over n log of ft as the first term, okay, and the lower order terms, which I will just write as a little o of 1 over n. So in particular, when n goes to infinity, we see that this converges to log of f of t, and then when you exponentiate, you get exactly what you want. Namely that this exponential of n, fn of t minus 1, converges to f of t, and this proves that any infinitely divisible distribution is a limit of compound Poisson distributions. Then, corresponding to these compound Poisson distributions, we also have the so-called compound Poisson processes. So in the above proof, we showed that if you take a characteristic function of the following form, this is a characteristic function of some compound Poisson distribution, which at the same time converges to characteristic function of your specific infinitely dimensional distribution. Now, on the other hand, we identified with each infinitely dimensional distribution a Levy process such that ft to the c is a characteristic function of that process at any time c. Right? So on this side, you have some Levy process such that f of t is the characteristic function of this process at time 1. Well, on the side of this compound Poisson distribution, we can also take the power c, which is again a compound Poisson. It's just that Poisson mean n has been replaced by nc. And we can ask, what kind of Levy process do we have on this side? Well, it turns out that we can give a quite explicit formula for this process here. And moreover, the Poisson processes that we discussed in the previous sections and a marking of Poisson processes comes into play here. Namely, you can define a process xn in the following way. We can first take a Poisson process phi, which is a Poisson point process, with the mean measure given by n dx on 0 infinity. So the mean measure is just a Lebesgue measure scaled by n. And then let's take independent markings of this process. So let yx for the points x in this Poisson process pi be independent markings with the distribution Pn. In other words, just IID random variables from this distribution Pn. And then we can define this process xn of c to be just a sum over all points in the Poisson process of these independent markings up to c. So over all points in this process up to c. Okay, so this process here is called the compound Poisson process. And we will now check that it is indeed a Levy process corresponding to this characteristic function of a compound Poisson distribution. And of course, this is almost obvious because in this definition of a compound Poisson process, we are summing IID random variables. And we know by definition of a Poisson process that when you take a part of the Poisson process on any interval, let's say on interval 0c, its cardinality will be Poisson with the mean given by the mean measure of this interval, and with our choice of mean measure, this is just NC. And the markings are coming from the distribution Pn, so this sum for a fixed C has exactly the compound Poisson distribution that we want, corresponding to Poisson mean NC and distribution Pn. Now, when you look at the increments of this process, it can be written as a sum of these IID markings over the interval between C1 and C2. And of course, by the properties of a Poisson process, we know that the cardinalities of intersection of our Poisson process with these intervals will not only be Poisson, okay, with the mean of this form, but they will also be independent for disjoint intervals. And so as a result, we get independent increments. Okay, because by this existence theorem for Poisson processes, these cardinalities are independent over disjoint intervals. And of course, the markings that we chose are also independent, which means that these increments above over disjoint intervals are independent. Now, the stationarity property is obvious here because these cardinalities above are given by these Poisson distributions with the mean that depends only on the length of the interval, right, and doesn't depend on the location of the interval. And then finally, continuity in probability. This just follows from the form of our characteristic function above. So we said that the characteristic function of this process xn at time c was just exponential of nc times this integral, which clearly goes to 1 as c goes to 0. So in other words, just like above, this means that our process at time c converges to 0 in distribution, and this automatically implies convergence in probability to 0. And of course, by stationarity, the same is true for the increment of the process in any location. So that means that just like all infinitely divisible distributions are limits of compound Poisson distributions, all Levy processes are limits of compound Poisson processes in the sense of finite dimensional distributions. Okay, so this finishes the overview of basic properties of infinitely divisible distributions and Levy processes, and in the next section we will take a look at characterization of all infinitely divisible distributions, or more precisely, characterization of their characteristic functions.